Oh man, Sarah, I woke up today and my neck just feels off and my whole aura feels off. And you know why?
Does your energy feel a little funky?
It just feels funky. And
I think I know why.
why?
Jupiter's in opposition.
Oh my gosh, Jupiter is in opposition. Just kidding, guys. That's astrology. We're here to talk about astronomy. Jupiter is in opposition, but what does that mean and what effect does it actually have on us? You want to start with what effect it has on us? Zero.
Yeah, so it just means that Jupiter it's the closest it's been to us in its orbit for this year, pretty much, and it's the opposite of the Sun. Opposition.
We're really creative with our naming and astronomy.
But it's not affecting us in any way. Apart from astrophotographers or like amateur photographers who want to take great photos of Jupiter, then it's fantastic.
The time is nigh because it's fully illuminated by our sun. And you can also see the 4 Galilean moons with binoculars.
Yeah, with your bare eyes, which is pretty damn cool.
It's amazing.
It's not going to mess up your aura or create any funky neck pains.
No.
You should see a doctor for that one.
But you know, let's do. Last week we touched on tidal forces a little bit, and you know, we just said Jupiter's in opposition, and our solar system is this complex, moving, system. I know I just said that twice. Sorry, guys, but the idea is that mass affects the shape of space-time, and that in turn affects how other objects move in it, this wonderful force called gravity. Well, the sun is definitely the most massive object in our solar system and has the biggest pull, which is why we have the orbiting planets.
Right.
But it was recently proposed that perhaps the solar activity that we see on the sun, all of this, the sunspots and this 11-year cycle, could actually be due to the planets pulling back on the sun.
That's pretty cool.
So I thought that was cool because maybe we don't feel like this, major effect on our auras or our energy.
But we still have some feedback effect on the actual solar system.
Absolutely. So that's pretty cool.
It is pretty neat.
Yeah, we see you, sun.
We see you.
But no, sorry, I got distracted. Anyway, let's go back to Jupiter. So it's in opposition. You can see it's very bright and you can see a lot of its features. But one of its key features is actually disappearing. Something that's been there since the 17th century, or recorded at least, is probably there for thousands of years even before that.
Right. So we're talking about the big red spot. And this is that beautiful red spot you see in all of the pictures. That big red spot, it's slowly disappearing, and the estimates are that because it's just a big giant storm, so you can imagine it's like almost like a hurricane but in a gas giant.
Yeah.
So it's dissipating, and so in 20 years we're not going to be able to see it, which is quite sad. So like this iconic image of Jupiter is no longer going to be accurate.
No, it's going to be different.
But have no fear.
Exactly. So when one awesome vortex disappears, it turns out there's actually many more. Thanks to the Juno spacecraft, we're getting these incredible views of Jupiter that we've never seen before. And it turns out that planet is just riddled with vortexes. Some of them even are deep, dark abysses. Again, we'll show you because me explaining it doesn't do it justice. But it's incredible that this planet is so complex, and we think of the Great Red Spot as the big kind of swirling storm on Jupiter, but there's many more.
So many more, and they're going to become more predominant as well. So as the Great Red Spot dies out, another vortex will eventually end up taking over in its spot, and so that's pretty cool.
It's amazing, and it just has to do with us learning more about the physics of these planets and the fact that it's not just one thin gas atmosphere, like relatively thin, like what we have on Earth, but thousands of kilometers deep, and so you have these upwellings and convection,
and all of those beautiful gases are mixing together to create those amazing colors that you see.
Yeah.
And so Jupiter is incredible, no doubt about it.
Yeah, look.
But he's not one of a kind, is he?
No, not at all. And it turns out that there probably are these gas giants, hot Jupiters even, they're called, in solar systems across our whole galaxy and probably in other galaxies. But how do we know that?
How do we know that? So astronomers are pretty good at searching for what we want to see. And so we continually build these amazing instruments and telescopes to hunt for the things we want to see. So we'll go into that a little later on.
Yeah. First, we're going to give you an introduction back to the blast off. So thank you so much for joining us again. I'm Dr. Rebecca Allen, and this is future Dr.
Sarah Webb. And if you like us, please hit that subscribe button down below.
Absolutely. And this is the blast off. So in this week's episode, we're going to continue our saga of looking for life, but this time beyond our solar system, and even looking for Earth analogs. And the reality is, we love to think we're special, but we really think, that there must be other life out there.
And there's some philosophical questions when it comes to is there life out there. So there's something called the Great Filter, and we'll link a good video below that explains it in more depth. But the idea is that either life is incredibly common and it gets to a filter point where it can no longer exist anymore. And if that's the case, you'd be very hard stretched to find life. Or life is still incredibly common and we're beyond that filter point, so intelligent life is not common, which is pretty cool. And so if that's the case, that means that we truly are special. But we really want to discover that, because statistically, we're not alone.
No, statistically, we're not alone. But, if you just think about Earth's history and how many mass extinction events there were, where it's not just like, a few life forms, but 90% of life on Earth completely gone. So basically then you're taking what small amounts of life did survive and its evolution, or basically, even imagine on some planets it's probably a hard restart. And so the idea is that, we have to consider all of this in time scales and relative time scales in different systems. But how do we find these other planets? Okay, this is one thing which I love to talk about, because we have all of these super gigantor telescopes on the surface of Earth, and then we have space telescopes. But have you ever thought about, why do we have to send New Horizons out to Pluto? Why don't we know what our outer solar system looks like?
It is really, really hard to see. And so even with our gigantor amazing telescopes, you can't focus it on Pluto and get a crisp image. We'll put the best image there was of Pluto before New Horizons, and as you can see, it's a little bit fuzzy. We don't understand any of the structure, and it's because it is so difficult to image things that are really far away and very faint. And so when we're looking for planets, you can imagine it's hard to find Jupiter. You can find it with your naked eye, but you can't see any of its structure. Imagine trying to find Jupiter thousands of light years away around a star. That's really hard.
And it has to do with the fact that, planets are different from stars. Stars make their own light because they're crushing together atoms in their core, which releases tons of radiation in the form of light. So they're these brilliant cosmic light bulbs, while planets can only reflect light. So just imagine any kind of scenario where you're in a dark room and you're holding a torch, and the further you are, the further the object you're looking for is away from your torch, the harder it is to see. It's the exact same thing for planets. But, okay, it's 2019. We know we found exoplanets. So, well, cut to the chase a little bit, but let's just talk about how we've started to look for exoplanets and how the first exoplanets were found.
So we'll start with the most logical one, is just to look, right? To take a telescope, point it somewhere and look. And so this is called direct imaging, and you don't just point a telescope and see the planets. You have to use something called a chronograph that blocks out the center light from the star and hope that you can see reflections of the starlight bouncing off the outer planets. And this is really successful. They've found quite a few planets doing this, but the majority of them are very, very, very large hot Jupiters. So massive gas giants very close to the sun. So this is great for finding planets and confirming that planets are in fact common, which is good. It means that that filter system might just be past us, but It's not great for understanding if there's any Earth analogues out there. How rare is Earth?
Right. Yeah, so that technique only works for planets, which are gigantor. Did you know that you can fit 1,300 Earths inside Jupiter? So again, teeny weeny. And these hot Jupiters, they're normally within the orbit that Mercury is to our sun. So very close to that light source and very large. Okay, well, we talked about last episode finding life on even our Jupiter. Finding life on a Jupiter which is tidally locked with its star because it's super duper close. Even even lower probability. Okay, and so we want to look for things which are a bit further out in their orbit from the star in what we call the Goldilocks zone. So when we're looking for Earth analogs, we know what makes life thrive on Earth. Water, having this great atmosphere with things that we breathe and that plants can help replenish and volcanoes help replenish. So we want to look for all of those signs. So the next thing that can be done is, remember we were just talking about gravity. Well,
we can use that. So there's a method called the wobble method. Wobble. So like Rebecca was saying earlier, that our planets orbiting our sun might be causing this solar cycle.
Yeah.
We can actually measure the sun, if we were to measure our sun wobbling a little bit with the planets orbiting around, and we can do that to other stars. So the way we do this is using spectroscopy. So we take the light that we're seeing and we split it into all of its thousands of wavebands, and we look for emission and absorption lines. And we do this again and again over time, and we see if those lines are shifting a little bit, and we can see if the star is wobbling to and from. We'll insert a pretty video here of what that wobble would look like with the planet orbiting around.
That's right.
But with this, it's a lot more sensitive to detecting things that not only are very close and very big, but are normal-ish sized rocky planets, which it's also been really successful in finding as well.
So now, again, hot Jupiter's still the main thing that you're picking up because
just a little further out.
Well, again, because it's like that minute wobble. Okay, something which, so now we said you could fit, over 1,000 Earths in Jupiter. Well, just you can fit over that many Jupiters in our sun.
Yeah.
So again, the ratio between those two is still quite unbalanced, and so even then that little detection, that wobble, is quite small. And so the smaller the planet you get, the smaller the wobble you're going to get.
And it ends up falling into the error region of these spectrographs. So no matter what you do in science, you always have error and uncertainty.
Yes.
And especially on ground-based telescopes, because we're dealing with the atmosphere, which is like this big, like Rebecca said last episode, this big ocean above us almost, of all these particles and winds and pressure. It is so hard to get really precise readings. And so to get the precise readings that we need to really detect these fine planets, we need to go into outer space.
Absolutely. So like we said, the other thing about the wobble method is this is what we call short orbit planets that you're going to detect. So a lot of these, unless the star is much different from ours, which we'll go into a little bit more later, they're going to be too close to be in that Goldilocks zone. So you know what? Hooray! Awesome job, guys. These methods found exoplanets. Okay, the Doppler and the Doppler shift and this wobble, that was the first technique that found more than one or two exoplanets. So that's amazing to be able to confirm that.
It is, and it means that planets aren't rare, which is pretty awesome.
They're not.
But is Earth rare? And that's what we really want to understand.
That's what we really want to know. So to give this a little bit of context, was how did we come up with this next method that we're going to tell you? I was doing some research and I found this amazing historical fact that I wasn't aware of. So around 200 years ago, okay, this is when we were still trying to understand latitude and longitude and this exact scale of our solar system. And so early, explorers, they would want to know, how do I know exactly where I am on Earth? And
I still don't know where I am on Earth.
And that might seem like, why are we bringing this point up? But the solution to understanding, where exactly, I guess the idea is, we knew that we're one astronomical unit away from the sun.
Yes.
But exactly how big is that? All right. And so that was a measurement that wasn't really well understood just 200 years ago. All right. And the way that that was actually addressed was that an English astronomer proposed, okay, well, you know how we can do this? There's a celestial event coming up, and we can use that to measure the angle where we see that event on Earth, and then we can go work backwards.
Yeah.
Geometry! We had to sing. We got to do a little singing moment. So what they did get to see was the transit of Venus. And this is really amazing because, you know, we're in the inner solar system, but there's planets, Venus and Mercury, that are in between us and the sun. That means at some point in their orbit, they cross in front of the sun. And we can see them being silhouetted on as they move in front of the sun.
Which means that if we are really precise in our measurements of how much light is coming off the sun, that will dip a little bit. Just that little planet passing in front of it will take a few percentage off.
That's right.
Which is exactly how we get to our next method, which is the transit method.
The transit method. So, a la the transit of Venus. Now, okay, we know Venus is there. We can see Venus. Again, you can see it with the naked eye in the early dawn or early dusk. But if we couldn't see Venus, we could still detect its presence indirectly. So now the idea is, you know, the wobble method is an indirect detection.
Yeah.
We're not actually seeing the planet.
We're just inferring that it's
We're
there.
inferring that it's there. And so the transit is another way of indirect detection. And so, you know, astronomers and engineers came together and they're like, well, if we could see the transit of Venus, why couldn't we use this method to look for exoplanets around other stars? And thanks to Kepler's laws of planetary motion, that information we get from the light being blocked can then be used to understand more about the planets.
We can figure out its orbit, we can figure out its mass, and we can even figure out how many times that is its orbit.
That's right.
So we can figure out its orbit and we can figure out its mass, all from just this little shadow passing in front of a star. But to do that, like we said before, you need to go into outer space because of the atmosphere. Because any measurement you make on Earth, a lot of the time, it's within errors. Any blocking out from a planet is within errors. And so we shot this amazing Kepler mission out into space, and Kepler is really no longer doing any science. But
no, it's officially done. But it has done enough.
It has done so much. It has found over 6,000 planets in its time, which is pretty incredible. And all it did was just stare for its first period. It just stared at a star field and measured what their light was doing. And what you can see, we'll put some beautiful light curves up, is when a planet passes in front, you get this beautiful dip. And from that dip, you can understand so much physics. And not only are you detecting planets from this, you can even detect moons around planets. So even though we have all of this information on all of these different planets we've found, we don't have our Earth analog yet, or our perfect, this is maybe where other humans exist or other intelligent species exist. But we can take all of these planets we have found and do some statistics on them. And so that uses my favorite equation, which is
the Drake equation.
And it's this pretty cool, hideous looking thing that takes into account all of these different values of how long should a civilization live and how close to the star should they be, and all of these different factors. And if you take this equation and you plug in all of the different values that we think we know, and we don't know all of them quite yet because we are only going off humans. But
that's right. We're going off our perception.
Our sample size of one.
And we won't get too philosophical, but the idea is, you know, we're doing the best we can with the way that we're able to take in the world around us. So yes, the Drake equation may be flawed, but you know what? It does a darn good job because it has like a jillion variables.
It does have a jillion variables. So we plug in for those jillion variables and we find that in our stellar neighborhood of just, you know, a few thousand light years around us, if we take that 1 in 10 planets found could be Earth-ish, whether it's rocky, whether it's close, just something about it could be Earth-ish. There's 800 planets in our stellar neighborhood that could be habitable, which is pretty cool. And that's a lot. And that's just in this tiny stellar neighborhood. So then if we zoom out to the Milky Way, which is the galaxy that our solar system lives in, so the Milky Way is this big, beautiful spiral galaxy, and it has over 300 billion stars in it. So if we do, like,
the number just blows me away every time I hear it.
300 billion, and that's we're not a big galaxy either. We'll get into that more in later weeks, but we're pretty damn average. And so we take these 300 billion stars.
Just an average planet around an average star in an average galaxy. Probably average intelligent life, too. Sorry, I digress.
So we take all of our averages, stick them in, do quick math, and in our galaxy alone, we should have 20 million planets that could have life. 20
million.
Which is insane, but that's not cool enough for me.
Okay.
Because the universe is not made up of one galaxy. It's made up of many galaxies. So
maybe like a few hundred billion?
Maybe a few hundred billion, even up to trillions, because we don't really know how big the universe is. We'll touch on this more in its whole own episode, because that is a mind explosion. But if we take the rough number of, there's probably about 1 trillion galaxies, whether we can see them in our observable universe or not.
Okay.
Do some quick math. We assume that all the galaxies are like the Milky Way, which is a big assumption because some of them are really big, some of them are really small, but we'll take the average again. Average planet, average galaxy, and you find that there's a possible 6,000 trillion habitable planets just waiting there.
But
that's huge.
It's huge. And look, they could be habitable, but I want to know, what's the probability that there is an intelligent civilization on that planet just waiting for our very advanced radio signals to reach it?
So that is where we get a little depressing.
Okay.
So you can imagine that humans have only existed for the last few 100,000 years. That's not a very long time in the scale of the universe.
No, it's really not. It's kind of a blip. And, you know, like we were talking about earlier, this idea of all these mass extinction events. Well, what if we, what if we just miss this civilization by, well, cosmically speaking, a few million years? That to us is eons.
Yeah.
But again, not really in the cosmic scale of things if you think about the fact that our solar system is billions of years old.
Yeah, which is crazy.
It's insane.
So this is where our odds of contacting any intelligent life come to a bit of a halt, because we are also limited by the speed of light. And the reason we're limited by the speed of light is because when we send a radio signal, or if we receive a radio signal, it can only travel at that 3 times 10 to the 8 meters per second.
That's right.
Which is mighty fast.
Sure.
But when you have a giant galaxy and a giant universe, it's not that fast.
Stuff is really far apart. And so the information we can send and receive is bound by the speed of light.
Right. And so our closest star to us is
the sun. Sorry, I had to.
No, it's true. Our closest star that is not the sun to us is 4 light years away, which, seems pretty reasonable. 4 years traveling at the speed of light. But that's our closest star. Yeah. And then if you get further and further and further out, you're getting to thousands of light years away.
Yeah.
And so it's a very low probability that life, any intelligent life, formed on the same time scales as we did.
Sure.
Because, again, as Rebecca was saying, to get here, we had to go through mass extinctions, we had to go through climates, we had to go through like this crazy evolutionary process, which won't be the same on every planet.
No.
So that's where we get a little dull, but it doesn't stop us trying to look.
Absolutely not. So we kind of, want to touch on, what is being done, because the reality is it doesn't hurt to try to look, and we have the technology to do that. So there's a program called Breakthrough Listen, and it actually uses one of the incredible radio telescopes here in Australia, the Parkes Radio Telescope. And the mission itself is broken up into several different parts, but one of the first ones is to look around us in our solar neighborhood at stars like our sun, looking for radio signals which are very, very strong and probably unlike anything we've ever detected before.
Right. We're looking for that signal in the noise. We're trying to find if anyone is beaming us a signal, because that's a possibility.
Yeah.
Or we're looking for signal leakage, which sounds pretty cool, but we're actually doing it right now. You're doing it right now. You're leaking signals. And this is where it gets difficult again, because we only started leaking signals, roughly about a century ago. And we're going to pretty much stop leaking our signals in the next century once everything becomes digitized and satellite.
Yeah.
It's more directed. We're not doing our analog.
No, it's just
signals.
Not this broad, signal being sent. It'll be very laser focus, probably literally laser focus.
Yeah. And so if we take us, for example, in the span of about 200 years, we've gone from emitting all of the radio signals to emitting nothing. And so that means that we have to catch a civilization like ourselves in that peak of them discovering radio, re-emitting, and then moving on to the digital age.
So the probability drops even lower. And this is what I always like to tell people. Is there other life out there in our galaxy? Heck yes. And there's probably even microbial life in our own solar system, or there could have, in the history of our solar system, there's definitely other microbial life. Is there other intelligent life out there in our own galaxy? Probably, definitely yes. Will we ever get concrete evidence or detect it?
Probably not.
Probably not.
But isn't it the cool thought that from everything we know and understand, we can say that there probably is intelligent life out there? There's even a planet probably just made up of dogs. That helps me sleep at night.
And if that doesn't exist in our universe, it certainly does in a parallel universe.
Which is something we'll touch on in a later episode.
No, I just, real quick, before we wrap up, I want to bring it up a little bit since we're like, oh, we're ever going to detect intelligent life? Probably not. Well, we are detecting cool kinds of different life on Earth. And recently I read a story that on the, in the very dark abysses of our oceans, where we're continuing to make, these discoveries, the idea, that we know more about our solar system and other places in our own ocean is very much real. Yeah. And we're learning new stuff every day, which, little public service announcement is why it's important to protect our oceans, because we don't actually know exactly everything that's in there. One new discovery, though, taken from soil samples from deep down on the ocean floor, found evidence of these tiny, again, little microbes that have probably been around for millions of years, probably only reproduce once every 1,000 years or so. That's a little depressing. But, the idea is that they could have been they could be some of the earliest life forms on our planet, and they still exist.
That is pretty cool. And they could have even been the very early life forms that introduced the building blocks to the rest of this evolutionary heaven that we live in.
So this idea of life and, all of these different organisms and it persisting and then evolving into, the forms like us or dogs or kitty cats or apes, it's incredible. And there's just so much more that we want to learn. And so we're going to keep looking for more of these Earth analogs. Hopefully we'll find one soon, and then we're going to get more information about it. So it's pretty cool.
It is. So hopefully we brought you some joy, and hopefully you can go to bed knowing that there's aliens out there somewhere in the universe, but they're probably never going to know we exist.
No, and that's a great ego check, I think, as well.
We're not that important if the aliens don't know we exist.
No. So, but look, there's tons of cool astronomy stuff we want to talk about with you guys. And so, in the next coming episodes, we're going to touch on some of that. And we're going to get into a little bit more of these things that we hinted at today, these amazing things called galaxies. So we hope you'll join us. Please, if you have any topics you're super interested in hearing about that pertain to astronomy, not astrology, please
let us know.
Please let us know.
Because we'll pretty much dive into anything. Did someone say multiverse?
What? Awesome. Thanks, guys. This has been
The Blast Off.